Now, this is Lopitas Rule. Please mind the way you write it. That H must always be capital. That H must always be capital. So even if you write it in the middle of the sentence and you have small letter L, this is still capital. Ha ha ha! Never forget, Mr. Chang is in the group now. Now that means 3 of us. People that write rubbish when they see Lopitas Rule. Okay, we use this to find limits of what we call indeterminate forms. Look at the word indeterminate. Indeterminate, determinate, determine. Okay, things that we cannot find. Okay, things that looks impossible. Things that looks like it does not exist. Okay, those forms, those rational functions that looks like their limit do not exist. Although when you plot the graph, you can always find the limit. But then when you try to find all the techniques of limits that you have done so far, nothing works. But the graph tells you there's a limit. But then on paper, you cannot do anything. It's because you don't have all the tools yet. I told you then, I said we're still going to talk about something later after differentiation. So now this will make sense because it involves differentiation. How the whole thing came about, we won't talk about the proof behind it. We're just going to state and use the results. Okay? A proof is in your textbook. You are welcome to go ahead and look at it later. Okay? Just for sake of knowing. Now, there are 3 major forms, indeterminate form you will encounter. I'll write them as a note, but let me discuss first. If you try to evaluate the limit and you get 0 over 0, this is one form. For example, you're trying to find limits of maybe x divided by, what can give me that? Let's say, as x tends to 0, of course, of maybe, let's say 3x. No, it will cancel. I don't want to say 3x. Exponential x will not, okay, exponential x minus 1. If I do what we know, property of limit, you can separate them, limit divided by limit. But the above gives you 0, the below also gives you 0. That is one form. You get what I mean? So that would be 0 divided by exponential 0 minus 1, 0 divided by 1 minus 1, 0 over 0. Uh-oh. But it doesn't mean when you plot this, you won't see the graph as x gets close to 0 to be approaching something. Am I making sense? So that's one. The second is when you have infinity over infinity, both positive and negative, of course. You might find yourself in a situation where you have infinity over infinity. So take, for example, we are trying to find the limits as x tends to infinity of exponential x plus 1 divided by exponential x minus 1. Okay? This will look like, oh, exponential x as 10 tends to infinity is a big, very big. It will continue to explode. So this will give you infinity at the top, infinity below. If you try to separate the limits, then this is another indeterminate form of the limit. The last is when you have a product of 0 and infinity. So take, for example, the last one looks like this. Or it could be like this. It doesn't matter which one comes first. So for example, limits as x tends to maybe infinity of x exponential negative infinity. Negative x, sorry. If you separate by product, limits of the first one, limit of the second, you know, property of limit allows us to do that, right? This will explode, right? The limit of this will be 0. Do you agree? Like this, exponential negative x is 1 over exponential x. As this explodes, 1 over that move closer to 0. So that is why we say exponential negative x approaches 0, when x approaches infinity. But exponential x approaches infinity when x approaches infinity. Remember, exponential is 2 point something. So if you continue to increase the power of a number greater than 1, it continues to explode, it diverges. Does that make sense? But if you have it the other way around, the reciprocal, your denominator continues to be big, the whole fraction continues to be small and small and small and becomes 0. That's why we say this approaches infinity when x approaches infinity, but this approaches 0 when x approaches infinity. The reverse is the case. If x approaches negative infinity, this approaches what? Say that again? 0. So just pretend you are substituting, but you are not actually substituting. So when x approaches negative infinity, this approaches 0. When x approaches negative infinity, this approaches what? Infinity. So it's the other way around. Do you understand what I just said? Nakita? Okay. So we have 3 forms. The form that leads to this, the form that leads to this, and the form that leads to this. Both of these are kind of connected. Why do I say that? If you have infinity times 0, you can say infinity divided by 1 over 0, such that the 0 went back later, right? Which is more or less infinity, infinity. And I could do the same here and get something that looks like this. So both of them are kind of connected, but we don't need to talk about how they are separated. So, Lopitas Rule has been proved that the limits of a function like this, as long as it falls into this category, will be the same as the limit of the rate at which they change. Which means, if you find the rate of change of the functions, this time around we don't use product rule or quotient rule. If you find the rate of change, which means when you differentiate, what you will get eventually is still going to be the same. So for example, if I differentiate x, I get 1. I differentiate that, I get exponential x minus 0, which is exponential x. And I find the limit as x tends to 0, I get 1 over exponential 0, which is 1 over 1, which is equal to 1. So even though this looks like impossible to do, actually it approaches 1 as x approaches 0. Let's see that on the graph and see first, before we now discuss. I write the formal definition. So the idea is, if it falls into the indeterminate form, differentiate. Differentiate once, try it again. If it doesn't work, differentiate again. Because there's no limit to how many times you can differentiate. Understand? Because the Lopitas Rule talks about, let's see. The Lopitas Rule talks about having, okay, let's check this first. X divided by exponential x minus 1. As x moves close to 0, right? As x tends to 0, you see? Either from the left or from the right, where does the curve move close to? Can you see that? If you are coming from the negative side, as you are moving close to 0, this dude is approaching 1. If you are coming from here, it's coming from wherever it's coming from, and it's coming close to 1. But if you do your direct substitution that you've always done, it tells you it's impossible to calculate. But practically, it tells you there's something there. This is how our Lopitas Rule helps us. Understand? So we differentiate, and it works. So if you have even the form that looks like a product, don't apply product rule. Can change it to quotient. Quotient in the sense that if I have x exponential minus x, I can write it as x divided by exponential x. Then I can do the separate derivatives. And after one derivative, it doesn't work, I try it again. Lopitas Rule says the limit of f over g is the same as x tends to some a, provided the two are differentiable anyway. It's the same as the limit of their derivatives. I'll write that formally now. Does this sketchy explanation make sense to us? All right. Let me give you a proper notes and definition. And this is everything about property of curve differentiation guess what? We actually did, within this short period of time, we did, let me see how many chapters. Chapters 15, 16, 17, 18, and 18. 3 chapters you have done so far. Like, that's huge. And I was looking at it, I'm like, oh my God, these guys have done. From page 399, by the end of today's class, you will have covered up to page 504.
And all that's good.
That's a lot. All that will not be in the test. But of course, they will send their representatives to the test. Okay? But I don't think, if you don't see it as different chapters, you see it as just idea of differentiation. It's better that way. Understand what I mean? All right. I'm like, what? Page 504? Like, oh my God, they've done a lot.
Imagine we get one question.
Okay.
That actually scares me more.
Let me present the indeterminate form properly for you. First of all, why do we do this? That. So we use this to evaluate limits that seems not to exist at first, but when you look at it graphically, oh, this limit actually exists. Why am I not getting something? Okay? Most of the time, these functions come in form of a quotient. Can you see? Because of them. Can you see now? So 1. Maybe I put it in tabular form. It's easier. I just use the formats on the book, just to put it in tabular form. So the forms and their description. This is when the limits for limits as x tends to a of f of x over g of x, where f of a is equal to g of a is equal to 0, not where the limit is equal to 0 each. Okay, that's one form. This is for limits where individual limits gives that. Maybe not exactly how it is put for you. You can read further in your book. This is for limit of products. Where as x tends to a, f of x tends to 0, and g of x tends to infinity, or f of x tends to infinity, and g of x tends to 0. So these are the three indeterminate forms that we can have. Charlie, it is saying plus or minus infinity. Plus or minus infinity looks like 8 that is about to trip, but that is sleeping in class. It now looks like a sleepy 8. Like when Nakita doesn't have a that will be sleeping. That would not be Nakita, that would be Nakita complement. Opposite of Nakita. Ready? So the Lopitas Rule itself. Let's f of x, g of x, real valued functions. Such that f prime of x and b prime of x exists at some point x is equal to a. If as x approaches a, f of x approaches 0, and g of x approaches plus or minus infinity. No, okay, g of x approaches 0, or f of x approaches plus or minus infinity, and g of x approaches plus or minus infinity. It could be a mix or a mix of both. f of x or g of x as x tends to a will be the same as the limits of the derivative provided this is not equal to 0 or infinity. Evaluate. Everybody, please pay attention. This is a summary of everything we've been talking about. If these two functions are differentiable, that is, you can differentiate them. Okay, they are differentiable at the point A. So that as x tends to A, as x approaches A, the two functions approaches either 0 or infinity or a mixture of both. If we are interested in the limit of their quotient, remember, as x approaches this, they approach something that we give an indeterminate form. This limit will be the same as the limit of their derivative, provided this limit exists. If it doesn't exist, we differentiate again. Now, how does that make sense? Now, let's pretend this derivative here is another function h and t. So which means your problem is back to this. So if these two are differentiable, at this point again, it means you can still differentiate more. Because it doesn't say your derivative is somebody else's starting point, right? If you differentiate 3x squared and you get 6x, well, without this can exist as a function on its own, right? It doesn't have to be related to that. Understand what I mean? So this is why you can differentiate as many times as possible in Lopitas Rule until you can clear the indeterminate form out. I would not expect this to be more than 1 or 2 derivatives for now. But there's a question that we will do in general. An example is in your book, but I will do the reverse of that so that you have 2 ways to look at it. Anyways, so quickly, if you look at this one, if we put x is equal to 0, cos x is cos 0, which is 1. Right? So at the top you have 0. 0 squared is 0. So that gives you the 0 over 0 indeterminate form. Right? So this, so since the limits of that, of course, is the same as this, which is 0, okay? We have the 0 over 0 indeterminate form. Of course, this doesn't have to be put in this form of description. It's just for you to understand what we are doing and how we got to where we are. Someone texting you in my class?
Grandma called me.
Oh, okay, Grandma, you are busy now. Sorry, Grandma, is busy now. Okay, she can't hear me. Okay, so that gives us that. So we apply Lopitas Rule. Applying Lopitas Rule, I'm just writing all these details so that when you are reading it on your own, okay? Applying Lopitas Rule, the original limit will be the same as the limits when I decide to differentiate these functions. When I'm doing the second example, I won't be this descriptive. This is just, if you forget something, you have something to look at. That's what Lopitas Rule says. You can see, I haven't substituted, so I'm still going to continue carrying along the limit. So which means I have the limit as x tends to 0 of derivative of this is 0, derivative of that is minus, so that's minus sine x. Agree?
Yes.
Right? What? Oh, 0. I didn't get enough sleep. That's what Callista would have said. Okay? So this is limits. Then I have sine x divided by 2x. Do you see something? 2 is a constant, yes?
Yes.
1 over 2 limits sine x divided by x. Did you see something here? What's that? Say that again. 1. Fundamental trait limits, right? Theorem on the limit of that trait function. Half times 1.
Oh.
Why is that half? Because we know that limits as x tends to 0 of sine x over x is equal to 1. We've done that before.
Yes.
Okay? So Lopitas Rule solves most of our problem for us. Let's see this function in the graph. So give me the numerator, 1 minus cos, yes? And denominator,
Remove the e.
uh-oh. Can you see? Whether it comes from the left or from the right. Did you see that? It approaches 1 over 2. And ordinarily you think, oh, it's not possible to be done. It's possible. Okay? Now, can I ask you to try, please, if you don't mind, you can leave space because of our time and copy later. Just attempt to start with. Then we will do it together in 3 minutes if you're not able to figure it out. Try limits x tends to infinity you don't need to state which indeterminate form it is. It's just for my explanation. Alright? Limits exponential x divided by x. Quickly, try that. Then 3. Let's take it one by one. We'll practice more of this on Saturday. you're done, raise your hand. Number 2.
I think so.
You think so? Can I see?
Like, I'll take it out.
You're not done, mister. When you
No,
finish,
well,
tell me.
Let's eat soon.